Hi there, Kermit the Frog here to finish our talk up on the gas laws. So tonight we're gonna go ahead and start with Dalton's law. Okay, here's Doc.
All right, so let's go ahead and finish up our talk on the gas laws. So we're going to cover Dalton's law, then we're also going to cover kinetic molecular theory, and then also Graham's law of diffusion. So the first thing we want to do is go ahead and remind yourself about ideal gases. And our assumption is that the gases do not or attract one another. Okay? So if the gases do not attract or repel one another, we can say that all the gases in air are independent of each other. They're acting independently. So that means that the total pressure that we would observe of air, like we've been measuring in lab the past few days, is actually just a sum of the pressure of each gas: nitrogen, oxygen, argon. So what that means is we can write that the total pressure is equal to the sum of the pressures. So you can also write it like this, that P total is equal to the sum, so I equals 1 for P sub I to the nth term. And that's just writing this out right here. P1 plus P2 plus P3 all the way out to plus P to the nth term. So it doesn't matter how many components you have. You can just take the sum of all the partial pressures of the gases to get the total pressure. So we can use the ideal gas law to determine the pressure from each gas. So if you know the partial pressure of gas 1 or component 1, we can just rearrange PV equals nRT in terms of P1. So P1 is equal to N1 times the quantity of RT over V. We can also write out for P2, well, that would be equal to N2 times RT over V. Well, why do we not put subscripts on T and V and R? Well, R is easy to explain. R is a constant, so that's going to be true for all of the gases if they're exhibiting ideal behavior. So, well, what about T? Well, if we're assuming that the gases are not attracting or repelling each other, that they are in some container, they're in some vessel, we can say that they all have the same temperature. Well, if they're all in the same vessel that's contained and it all has rigid walls, then we can say that it has the same volume. So the only thing that's different for these gases would be their partial pressures and therefore the amount of moles that are present. So we can rewrite Dalton's law in terms of the moles. You can substitute using the ideal gas law, that the total pressure is equal to the sum of the moles times RT over V. So I would urge you to go through and write out a proof for this, maybe out to the N sub 3 terms, so truncated after 3 expressions, but go ahead and prove to yourself that this is a good expression. So sometimes you're given a total pressure, but you don't know the partial pressure of each gas. So the way that we can find the partial pressure of each gas is to use a mole fraction. So think about all the different ways that we've expressed concentration. We've done molarity, we've done mass percent, volume percent. Well, here's mole fraction. So the mole fraction is the moles of the component that you're interested in over the total moles in the mixture. So if we had, let's say we had nitrogen and oxygen as our primary gases. If you wanted to know the mole fraction of nitrogen, you would have to take the moles of nitrogen divided by the total moles. So you'd have the moles of nitrogen plus the moles of oxygen. And this would give you a mole fraction. A mole fraction will not have any units because numerator has units of moles, denominator you add those together, has units of moles, so the units cancel out. So a mole fraction is dimensionless. So we could write the mole fraction of 1 in terms of being n sub 1 over the total number of moles. Well, we can also substitute in using the ideal gas law. So this is for the partial pressure. We have P1 times V over RT, because we're going to substitute in for N1. This is just rearranging the expression from the previous page. Okay, so we'll have P1 times V over RT, and then we can substitute in for the total moles. Because remember, if you have PV equals nRT, and you rearrange to solve for moles, you'll have N equals P, and since we're having the ith term here, we'll go ahead and factor that out. So it'll be N is equal to V over RT. So that ends up giving us this expression, that you can also find the mole fraction from the partial pressure, P1, and then the total pressure. So a more common way to write this expression is that your partial pressure of component 1 is equal to the mole fraction times the total pressure. And this is another way that we can use Dalton's law. So let's go ahead and try to calculate the partial pressure from a mole fraction. So here, what we're going to do is we already know the mole fraction. So if we want to know the partial pressure of N2, what we can do is we can take the mole fraction, which here is 0.7808. Remember, that's dimensionless. It doesn't have any units. Multiply by the total pressure. And the total pressure here is given to be 760 torr. So keeping in mind sig figs here, we should end up with 3 significant figures. This should end up being 593 torr. All right. The other way that you could write this out, if you want to see the variables plugged in, is you would have the partial pressure of nitrogen is equal to the mole fraction of nitrogen times the total pressure. So make sure that you would be able to calculate this by yourself, because you're going to have to calculate a mole fraction by yourself, but more likely than not, you would be given a total pressure if you're asked to find a partial pressure. Okay, that's more or less what Dalton's law is talking about. It's saying that the sum of all the partial pressures equals the total pressure because the gases do not attract or repel one another. So the total pressure is given by the sum of all the gases. Here's another example. So this says that at an underwater depth of 250 feet, the pressure of a tank is the pressure is 8.38 atmospheres. What should the mole percent of oxygen in the diving gas be for the partial pressure of O2 in the gas to be 0.21 atmospheres? The same as it is in air at 1 atmosphere. Okay, well, here what we're going to do is we're going to have to recall that we have, well, the pressure of 1, which in this case would be oxygen, is equal to the mole fraction of 1 times the total pressure. So it's asking for the mole percent, so we're going to find the mole fraction first. Well, we know what the partial pressure is. It's 0.21 atmospheres. We don't know what the mole fraction is. That's what we're trying to solve for. So we're going to not dissolve. What am I talking about? You're going to divide by the total pressure, which is 8.38 atmospheres. So this is good because the units cancel out because the mole fraction has to be dimensionless. And then since you're finding a fraction, you're going to have to end up multiplying your answer by 100%. And you should get this answer unless I made a mistake. Ah, pizza. That looks delicious. All right, let's go ahead and talk about diffusion and diffusion, and we'll talk about Graham's law. So you guys should have a decent background of diffusion. This is whenever something moves across a concentration gradient from a higher to lower concentration. Okay, so we can define the rate of diffusion as being the amount of gas passing through an area at a given unit of time. If you go on to take some more chemistry or physics, you'll eventually talk about effusion. And effusion will look something like this. It might be that you have a cell with a really small hole in it up here. Then let's say you put a solid sample in here. And then if you put this under vacuum and then in a water bath, you can actually sublime the solid. So the solid would go from solid to gas phase, and then you can measure the rate of effusion as the gas leaves the cell. And this is assuming that only one molecule comes through the hole at a time. So if this turns into a gas here, it could hit the top of the cell and fall back down. So only one molecule is allowed to go through at a time. So what we're going to be doing is we won't be finding effusion rates usually for a system that's isolated with a gas. We would find relative rates. So Graham's law of effusion says that the rate of effusion is inversely proportional, so that's what that alpha sign means, to the square root of the mass of its particles. So if we want to compare two gases, A and B, since they're inversely related, the rate of A to the rate of B would be equal to the square root of the molecular weight of B over the molecular weight of A. And this is assuming that they are at the same temperature and pressure. So let's go ahead and look at a sample problem. Calculate the relative rate of diffusion of oxygen compared to that of ozone. So let's think back to what what the expression shows us. It shows us that the rate of effusion is proportional to 1 over the square root of the molecular weight. So have an expectation. Do you think the species with the smaller molecular weight will effuse faster, or will the one with the heavier molecular weight effuse faster? So go ahead and make a prediction, and then try to set this problem up on your own, and I'll solve it for you right now. So if we know that rate A over rate B, I usually put the one with the smaller molecular weight on top. So I'd put the rate of oxygen over the rate of ozone. And that would be equal to square root the mass of ozone over the molecular weight of oxygen. So plug and chug, and you should end up getting something along the lines of 1.2. So the reason why I tend to put the gas with the smaller molecular weight on top is that it does effuse faster. In fact, here oxygen effuses at a rate of 1.2 times as fast as ozone. So the way to think about that is, so there's 1.2 molecules of oxygen effusing for every molecule of ozone, or 5 molecules of oxygen for every 4 molecules of ozone. So these are some of the types of problems that you might have to solve using Graham's law of effusion. Okay, so all the gas laws that we've encountered so far, they've more or less been talking about macroscopic properties that we can measure. Well, what actually happens at the molecular level, and how does that apply to what we observe at the macroscopic level? This is where kinetic molecular theory comes into play. And you'll see this abbreviated as KMT a lot. So, KMT is based on the following assumptions. And we've established most of the assumptions from the various gas laws. So, the first assumption, gas consists of tiny particles, either atoms or molecules, moving about at random. So that means that we can think about in a container, and this kind of goes with the second point, that the volume of the particles themselves are negligible compared with the total volume of the gas. So if we have a container here, and in this container we have two gases. We have our red gas, and we have our green gas. This is saying that the motion of these gases, this one might be moving to the right in the box, this one might be moving down. And there's really no rhyme or reason for why they're moving that way. And in fact, these gases you can think about as being points in space. We don't think about them occupying a given volume like a solid or a liquid. The gases just disperse to take up the entire space of the container. Okay, well, if these gases are acting independently of each other, there's no attractive or repulsive forces between the particles. So as these particles are moving along, they're going to keep running into the walls of whatever's containing them. Whenever they run into the walls of that container, these collisions are elastic. Well, what do we mean by elastic? We mean that no kinetic energy is transferred from the gas to the walls. Okay? And finally, the last thing from kinetic molecular theory, the last point is the average kinetic energy of all the gas particles is proportional to the temperature of the sample. And the temperature needs to be in Kelvin. Okay, and we're going to have an expression that shows this here in just a little bit. So we'll write an expression that shows that the average kinetic energy is equal to 3/2 RT. Which you don't need to know how that's derived right now, but we'll talk about it. You'll have to utilize it. All right, well, how does this relate to what we've learned so far? Well, with Boyle's law, we said pressure and volume are inversely related. So the gas pressure more or less comes down to, in your container, how many particles and at what force are they hitting the walls. That's what's measuring the pressure. So if we have a pressure sensor, a really simplified way of thinking about it is we have a gas molecule coming by and hitting it. Okay, so that might have, let's say that one has a pressure of 1. Well, if we add some more gas in there, or if we, let's say we half the volume, so then the gas has less room to move around, then there might be 2 molecules of gas hitting the wall. So then the pressure is going to double because it has half the space to work with. So at the molecular level, you can just think about the number of collisions and the forcefulness of the collisions with the wall. The next law that we'll talk about is Gay-Lussac's law. And this just says if the temperature is increased, the average speed and kinetic energy of the gas molecule is increased. So this is just like we did the other day. Whenever we put our flask into our water bath. So remember, we had our water bath here. And we had our flask submerged in the water bath. And then we heated it up. Fire. And then we cooled it down with ice cubes. And we were able to measure the effect that these ice cubes had for cooling the water, what happened to the pressure of the gas. Charles' law, which is the third experiment we did whenever we were able to adjust the volume with the syringe and measure the temperature as we kept the pressure constant. This just shows us that temperature is a measure of the average kinetic energy of the gas particles. We didn't do a lab utilizing Avogadro's law, but it should be fairly obvious that the more particles you put in a gas sample, the more volume you need if you want to maintain a constant temperature and pressure. Because if you are not having a flexible volume and you throw a whole bunch more particles in there, you're going to increase the number of collisions. And as the number of collisions increase, your pressure goes up, which in turn means your temperature is going to go up, so your kinetic energy would be increasing. And finally, Dalton's law that we just discussed today, that we said the sum of the total, or the total pressure is equal to the sum of the partial pressures. This just says that if everything's acting independently of each other, the identity of the particles in the gas is not relevant for the ideal gas law. So that's what taking these macroscopic laws and observations that we've made and thinking about them at the molecular level, what they're actually saying. So let's go ahead and look at a mathematical expression for the kinetic molecular theory of gases. Okay, so here's our expression. And this E sub k, that's the kinetic energy. So kinetic energy is equal to 1/2 times the root mean speed. Okay, so that's your average molecular speed. So, and what we'll find is that the total kinetic energy is equal to 3/2 RT. Okay, and that's factoring in Avogadro's number. So this is just another expression. I probably should have used K, a lowercase k here instead of R. So we're going to use 3/2 RT, and that's equal to 1/2 M times U squared. We think back to what kinetic energy, the definition of kinetic energy is in physics. Kinetic energy, if we're writing that in terms of velocity, is 1/2 mv squared. Okay, well, if we want to, we can rearrange the root mean square speed. So you'll see root mean square. You'll see that written a lot as this RMS. But then whenever you introduce that speed term U, so U sub RMS means root mean square speed. All right, so whenever we take, excuse me, whenever we take this term, we can plug in for the root mean square speed. We can have the square of the root mean square speed is equal to 3 RT over M. Okay, so how do we do that? Well, whenever we start with this expression up here, with the 3/2 RT over Avogadro's number, well, if M right here, this M, if we're looking at, that would be considering the mass of one molecule. Well, if we start to rearrange this term right here, and we are trying to solve for U squared, we'd multiply both sides by 2, so we'd end up with 3 RT over Avogadro's number times the mass of a single molecule equals the square of the root mean square speed. Okay, well, if we have Avogadro's number times the mass of a single molecule, that is going to equal the molecular weight. Okay, and again, because this is going to be in terms of kilograms. It's not going to be in atomic mass units. This is going to be in kilograms. So if we take Avogadro's number times the mass of an atom or a molecule in kilograms, we're going to end up with the molecular weight. So anytime we plug in a molecular weight into the equation, it has to have units of kilograms per mole, which I've highlighted right over here. So you have U squared, except our mass equals 3RT over the molecular weight. Take the square of both sides, you get the root mean square speed times the square root of 3RT over m. So R, we aren't going to use 0.0821. Now we're going to use the expression 8.314 joules per mole Kelvin. And remember that joules has base units of kilograms, meter squared, per second squared. So this is going to take care of a lot of our units on the next part. So let's go ahead and try an example and see what this looks like. Let's find the average speed of helium at 298 Kelvin. So we're going to go ahead and just start with this expression that U is equal to the square root of 3RT over m. So let's plug in. Let's see. Square root 3 times 8.314 joules per mole Kelvin. Then that's times the temperature, which is 298 K, all divided by the molecular weight. All right, well, what is the molecular weight of helium? It's 4.0 grams per mole. Okay, well, we need to convert that to kilograms. So go ahead and divide that by 1,000. Okay, well, let's take a look at our units really quick and see what cancels out. We can see right away the moles cancel out. Kelvin cancels out. The grams cancel out. So our units we're stuck with right now are joules per kilogram. Well, we know speeds are expressed in terms of a distance per time. So how's a joule over a kilogram going to give us meters or kilometers per second or miles per hour, something like that? Well, remember that we said a joule is a kilogram meter squared per second squared. Okay, and then this was all over a kilogram. So the kilograms cancel and we're left with meter squared per second squared. All right, but we were taking the square root of both sides. So if we take the square root, those cancel out, we're left with meters per second. You're going to get a very, very large number. So what you'll see is the average speed of helium at 298 K, which is room temperature, that an atom of helium is moving at 1.3 kilometers per second, or 3,000 miles per hour. So go ahead and plug that in your calculator. Make sure that you can get that. Let's check out a graph really quick of some average speeds of the gas molecules. Okay, so notice that they all more or less have a normal distribution here. As we're looking at the different gas molecules, why does helium have such a higher average molecular speed than water, nitrogen, and oxygen? Well, think about what we were exploring on this slide, okay? So we said that the root mean square speed is equal to 3RT over m, the molecular weight, that square root of that. So the denominator is the molecular weight. Well, the molecular weight of helium is about 4. The molecular weight of water is about 18. The molecular weight of nitrogen, 28. Molecular weight of oxygens, 32. So you can see that as the molecular weight is increasing, the average molecular speed is decreasing. Okay? So this would be a good example of a problem that we might use on the exam where we give you a graph and ask you to explain what the identity of an unknown gas is, or to arrange if we didn't have any labels here and we just labeled them A, B, C, D, and we ask you for the identity of C, and then we gave you a list of some possible molecules, and you'd have to figure that out. We'll cover this some more in class, but this is just a graphical representation of the molecular speed here for some different molecules. So something that you aren't really going to be tested over, but that you should be aware of. The ideal gas law works really, really well for approximating many things. It's a really good estimate. But the real gases will have behavior that differentiates a little bit from ideal behavior. So, what are some things that might contribute to this deviation? Well, the volume of the gas may not be negligible after all. So you might have to take into account the size of a large molecule, that it's no longer a point in space, that it's not just a whole bunch of points. Now you can think about maybe they have some sort of repulsion between them. Okay. We assume that no attraction between the particles. If you have a low pressure, that means the number of collisions with the wall is low. Okay, well, what happens if we had a volume that was this whole page, then we cut the volume to here? Then all the gas was forced into this small volume. Well, the number of collisions is going to increase inversely. Okay, so as the volume is decreased, the number of collisions is going to increase a lot. So at high pressures, these particles are now going to be a lot closer to each other. And as you get closer to each other, you start to interact with each other, whether you want to or not. Okay, so if you get closer to each other, the attractions between these molecules start to actually become significant if the distance is 10 molecular diameters or less. Okay, so if you had a molecule that was this size, okay, if we have another gas molecule the same size over here, no real attraction. But the minute that it starts to get closer, now these two are going to start to interact and they're going to influence each other. And there's a lot of equations out there. Probably the most popular one to use for beginning study on real gases is the van der Waals equation. And this looks, again, a lot like PV equals, or P equals nRT over V. But now there's some correction terms. And there's a term in here, A, that accounts for the intramolecular attractions. So what's happening as these things bump into each other? Are they repelling? Or are they attracting each other? And then the correction for a molecular volume. Okay, so if the gas is no longer a point in space. Okay, so let's think about this. If there's an attractive force between the gases, that means their pressure should decrease because these things are going to be closer to one another. So their volume term should be decreasing. If they're repelling one another, then their pressure should increase because their volume is going to be getting greater. All right. Well, that's it for the gas laws. So we will pick up again in class.